The night sky has always whispered secrets to those who take the time to listen. Somewhere out there, far beyond our own small blue world, a new light has caught the eye of the James Webb Space Telescope, a planet so familiar it feels almost like a reflection of home. Scientists say there's a 99% chance it could hold life. Imagine that. Another world where oceans might shimmer under alien suns, where something could be watching the stars just as we are now. Tonight, we'll drift together through space and possibility, following the quiet clues that hint at life beyond Earth. If you enjoy these quiet journeys through the cosmos, gently tap like and subscribe so we can keep exploring side by side. Far away in the constellation Leo, about 120 light-years from us, the James Webb Space Telescope has found something that could change how we see life in the universe. It's a planet with a soft warmth around a steady 120 degrees and an atmosphere rich with the faint signs of living chemistry. Scientists believe, with almost total certainty, that they found a world alive. The first hints came one quiet December morning, hidden inside an ocean of data. At Cambridge University, an astronomer named Niku Madhusudan studied the faint fingerprints of light that had traveled across space to reach his screen. In those fragile wavelengths, he saw a pattern that shouldn't have been there, a molecule called dimethyl sulfide, which, on Earth, is made only by living things. The signal was clear, strong, and nearly impossible to mistake for noise. The planet is called K218b. It circles a small red dwarf star in a zone warm enough for liquid water. It's much bigger than Earth, wrapped in a thick blanket of hydrogen that holds in heat and keeps its wide oceans from freezing. The air may be heavy, but the world seems balanced, warm enough for life, yet gentle enough for water to stay. For months, Madhusudan's team used the telescope to watch the planet's light fade and return as it passed in front of its star. Each orbit told a new story. First water vapor, then methane, then carbon dioxide. But when dimethyl sulfide appeared, everything changed. This simple gas, born of life on our own world, now whispered its presence from another. The numbers were astonishing, 99.7% certainty that what they saw was real. In science, that's almost a heartbeat of truth. If confirmed, it meant something extraordinary. Life might not belong only to Earth. The loneliness of our species, stretching through time and distance, could finally end. What makes K218b even more remarkable is its stability. Its thick hydrogen atmosphere spreads warmth evenly, keeping the planet calm and steady. Its red dwarf star burns cool and constant, far longer than our own sun ever will. Life there would have time millions, even trillions of years to grow and change, to become something we can barely imagine. This discovery also reshaped what scientists thought a habitable world should be. For decades, they searched for Earth's twin, a rocky planet circling a star like ours. But K218b isn't Earth's twin. It's something stranger, a super-Earth, larger than our planet, but smaller than Neptune. Until now, most believed such worlds were too heavy, too smothered in gas to host life. Yet this one has proven otherwise. Gravity there is fierce, about 3 times stronger than ours. A person who weighs 150 pounds on Earth would weigh more than 400 on K218b. But that same force may help life survive, holding the planet's air tight so it can't drift away into space, as happened long ago on Mars. The atmosphere itself is alien, made mostly of hydrogen and helium instead of oxygen and nitrogen. On Earth, hydrogen barely exists in the air at all. On K218b, it rains. This thick, light gas wraps the world in a kind of warmth we call a greenhouse effect, but not the kind that scorches. It spreads the star's gentle heat evenly, keeping even the dark side of the planet forever turned away from sunlight warm enough for liquid seas. The telescope's readings tell a story rich with hints of life. Along with dimethyl sulfide, scientists see methane, carbon dioxide, and water vapor molecules that, on Earth, flow through the breath and cycles of living things. The most curious part, though, is what's missing. There's no sign of ammonia, a gas that should fill a lifeless planet's air. Its absence may mean something is removing it, something alive. This quiet world around a distant red star may be more than a curiosity. It may be proof that life is not rare or fragile, but woven into the fabric of the universe itself. If living things can thrive in the thick hydrogen skies of a super-Earth, then the number of worlds that might cradle life grows almost beyond counting. Most of the stars in our galaxy are red dwarfs, like K2O-18, each perhaps with planets of its own. We may not be searching for another Earth after all. We may be learning to recognize her distant cousins, worlds strange and beautiful, waiting in the dark, alive in ways we are only beginning to understand. The James Webb Space Telescope isn't only a machine for looking into space, it's a window into time itself. Floating nearly 1 million miles from Earth, at a quiet place called L2, it sits perfectly balanced between the pull of our planet and the Sunday. There, in deep darkness, its huge silver shield blocks heat and light, keeping the telescope colder than even the surface of Pluto. Its golden mirror stretches about 21 feet across, built from 18 perfect hexagons, each covered with a thin layer of gold. Together, they catch faint heat from across the universe, light that no human eye can see. When the pieces align, Webb becomes so sensitive it could spot the warmth of a bumblebee resting on the moon. That's the power of infrared light, the invisible glow of warmth that carries the secrets of distant worlds. When a planet passes in front of its star, some of the starlight filters through the planet's air before reaching us. Different gases absorb different shades of infrared, leaving behind tiny patterns or fingerprints that Webb can read. Finding those signals is like trying to notice the glow of a firefly beside a 1,000-mile distant searchlight. The star K2O-18 blazes billions of times brighter than its small planet, yet Webb can still find the faint shimmer of life's chemistry hidden in its atmosphere. To do this, the telescope uses a tool called a coronagraph. It works by blocking the star's harsh glare, revealing the softer light around it. Computer systems then remove what remains of the star's brightness, leaving only the quiet trace of the planet's breath. It's like muting the roar of a jet engine just enough to hear a whisper beneath it. Detecting dimethyl sulfide on K218b pushed Webb to its limits. The signal was so faint that it took many observations, each gathering just a few fragile photons, tiny messengers that had traveled for more than 100 light years. Those few particles of light carried the story of another world and of the life that might be growing there. Webb also measured the planet's temperature, 120 degrees Fahrenheit, warm enough for oceans, cool enough for water to stay. This reading, accurate within a few degrees across such vast distance, stands as one of the most delicate temperature measurements ever made beyond our solar system. Behind every image and reading lies an ocean of data, sifted by advanced algorithms and artificial intelligence. Machines search for patterns too small for the human eye to see, building a bridge between raw numbers and meaning. The discovery of life's signature on K218b is not only an achievement of science, but of imagination. a sign of what happens when curiosity and patience stretch beyond the possible. 120 degrees, a simple number, yet it speaks of balance. It's the warmth of a summer afternoon in Death Valley, the heat of a human fever, the comfort of a hot bath. On that distant planet, it is the perfect warmth for life. Temperature decides everything. If it falls too low, water freezes and the spark of chemistry goes silent. Too high, and water escapes into steam, leaving behind only rock and dust. Between these extremes lies a narrow space, the habitable zone where water stays liquid and life can begin. Earth rests in this fragile middle ground, a cosmic accident that has lasted billions of years. K218b's warmth, though, isn't an accident. It's the result of a careful balance between its star's gentle light and its thick, hydrogen-rich air. The planet receives nearly the same amount of energy from its red dwarf as Earth does from the Sun, yet its dense atmosphere traps and spreads that energy evenly. The hydrogen acts as a soft blanket, keeping the heat from escaping, warming even the side of the planet that never sees daylight. This creates a world with no harsh seasons, no frozen poles or scorching deserts. Liquid water could exist across its entire surface, from the bright day side to the endless night. On Earth, temperature shifts shape our lives, forcing creatures to migrate, adapt, or hibernate. But on K218b, life could rest easy under steady skies. A stable climate would mean that living things there could use their energy for growing, evolving, and thriving, rather than simply surviving. And that 120 degrees? It's not just tolerable, it's ideal. In labs on Earth, scientists have found that life's chemistry can work smoothly even up to 250 degrees. At 120, reactions happen quickly, yet gently enough for fragile molecules to stay intact. K218b's perfect warmth is more than a scientific detail. It's a quiet miracle. In a universe where most worlds are frozen in darkness or scorched beyond recognition, this one glows with calm possibility. It reminds us that life doesn't just cling to the edges of chance. It flourishes wherever the universe gives it room to breathe. Dimethyl sulfide. The name feels like a puzzle, yet it points to something simple and deep. When the James Webb Space Telescope found this molecule in the air of K218b, it found a sign that, as far as we know, does not come from rocks or weather or any lifeless process. It found a mark that, on our world, belongs only to living things. Here on Earth, tiny ocean drifters called phytoplankton make dimethyl sulfide as part of how they live and grow. Marine bacteria make it, some algae make it, and a few plants do too. The gas then rises and helps seed clouds, shaping gentle changes in weather. No volcano, no simple chemical mix, no non-living system has ever been seen creating it. That's why its trace on K218b matters so much. Scientists call this kind of clue a biosignature, a chemical footprint that points to life. Oxygen can come from other paths. Methane can seep from rock. Dimethyl sulfide, as far as we know, does not. Its shape tells a careful story. The molecule links sulfur with two small carbon groups, and making that link usually needs special helpers enzymes that living cells build. On Earth, these enzymes are part of the sulfur cycle, a web of reactions that keeps our air and oceans in balance. Finding a similar molecule far away hints that life there may also use step-by-step pathways, the kind that take time to evolve. What startled researchers most was not just the presence of dimethyl sulfide, but how much of it seemed to be there. The amounts were far higher than a world with only a few tiny life pockets would make. That suggests a busy, living system at planet scale, not a lonely pond, but a whole world's air touched by life. If dimethyl sulfide can be measured from more than 100 light-years away, the biosphere must be large and active, with creatures small or complex breathing and building in ways that change their sky. This points to a larger idea. If life on K218b makes dimethyl sulfide, then it may rely on the same basic set of building blocks we do: carbon, hydrogen, oxygen, nitrogen, and sulfur. It hints that life's chemistry may follow familiar patterns wherever it starts. Not a rare miracle, but a path the universe likes to take. Science, though, is careful. It speaks in chances, not certainties. Even so, when the Webb data was studied, the story held firm. The chance that the dimethyl sulfide signal was real was put at about 99.7%. Think of flipping a coin 1,000 times. Getting heads or tails on any one flip is even odds, but getting the same result 997 times is so unlikely you would not expect it to happen by chance. That is the kind of confidence we're talking about. Researchers use a measure called sigma to express this. A 3 sigma result lines up with that 99.7% level. It means the signal is very likely real, not a random wiggle. This yardstick is used across fields, from finding new tiny particles to catching the faint ripple of gravitational waves. Reaching that bar for a world so far away took care and patience. The dimethyl sulfide signal is extremely soft, like a whisper in a storm. It shows up in the infrared at only a few parts per billion. To catch it, Webb had to measure the color of light with incredible accuracy, fine enough to be like judging the width of a human hair with the care you'd use to place a single atom. The team did not rely on just one look. They watched the planet again and again over months. Different tools on Webb saw the same fingerprint at different wavelengths, a kind of cross-check. Computers then combed through millions of data points, hunting for errors or hints of contamination, something from Earth, or a quirk in the instrument, or a strange non-living chemistry that could fake the signal. Each idea was tested and set aside. The simplest fit left standing was life making dimethyl sulfide. In the study of distant worlds, this level of confidence is rare. Many reports of molecules in exoplanet air come with lower certainty, just enough to publish and keep watching. Here, the 99.7% mark feels like a step change, a sign that our tools and methods have crossed an important line. When scientists say they are that confident about life on K218b, they are placing the claim alongside other well-tested truths. It stands with the strength of ideas we lean on every day. We are careful not to race ahead, yet the quiet message is hard to ignore. Somewhere, under a sky filled with hydrogen and soft starlight, life may be breathing and growing, changing the air above an entire world. For the first time, the evidence points past wondering. It points toward knowing. Beneath the strange skies of K218b, there may be an ocean unlike anything we know. It is not only water. It is water mixed with hydrogen, held under pressures that would crush most life on Earth. Yet, this ocean could be one of the most welcoming homes for life anywhere. The reason lies in the planet's chemistry. The thick hydrogen air does not sit as a separate layer the way our air does. It dissolves into the liquid below, blending with the water. That mixture stays stable across a very wide range of temperatures and pressures. Pure water turns to ice or steam outside a narrow band. A hydrogen-water mix can remain liquid from near freezing to well above the heat of a kitchen oven, giving living things a broad, gentle space to grow. On our planet, the deepest ocean trenches push down with a force almost 1,000 times stronger than the pressure at sea level. Most cells cannot keep their shape there. Their walls buckle, their proteins fall apart. On K218b, the dissolved hydrogen softens that squeeze. Think of it as a built-in cushion. Even far below the surface, the liquid can behave more like familiar water at milder pressures, keeping it friendly to complex chemistry and to structures that might otherwise fail. This ocean may also help the planet keep its air for an immense stretch of time. Earth slowly leaks gas to space. Over billions of years, it adds up. K218b's ocean acts like a giant backup tank. When hydrogen is lost from the sky, more can drift out of the water to replace it. The balance can last for ages, perhaps for spans so long they make human history feel like a heartbeat. A steady atmosphere means a steady climate, and a steady climate gives life room to plan for the long term. Hydrogen brings another gift: energy. Some bacteria on Earth can use hydrogen the way we use food and oxygen, but they are limited because our air holds almost none of it. In a world where hydrogen is everywhere in the sky and in the sea, organisms could breathe the ocean itself. They might power their lives with reactions that are rare here, but common there. If so, the main life forms might look invisible to our usual tests, which often focus on oxygen and on the green work of plants and algae. The dimethyl sulfide already hinted at could be just one voice in a larger chorus, signals from an ecosystem built on hydrogen chemistry, humming along in ways new to us. No one knows how deep this ocean goes. Computer models suggest it might reach hundreds of miles, far beyond our deepest trenches. Imagine layers upon layers of liquid laced with hydrogen, where temperature and pressure drift slowly and gently. Instead of swinging hard, such stability can let life try new forms. It could allow delicate structures to endure. Over long ages, that calm might open doors to complexity we have not yet learned to picture. This changes how we think about habitable. We used to look for Earth's twin: rocky ground, thin air, a sun-like star at just the right distance. K218b invites a wider view. A super-Earth circling a red dwarf may offer something even kinder. In thick hydrogen oceans, life might not only hang on, it might bloom. The friendliest places in the galaxy may be the most alien to our senses. Above the ocean, the air tells a story rich with chemistry. Where our sky is mostly nitrogen and oxygen, this one is a mix with hydrogen in charge. Methane drifts through its clouds. Carbon dioxide stacks into crystals in the high, cold layers. Where pressure climbs and carbon is squeezed, tiny diamonds can form and begin to fall. It sounds like a tale, yet it follows from simple rules: the right atoms, the right heat and weight, the right time. Methane is a special clue. On Earth, it comes from many living sources: swamp microbes, termites, even the stomachs of cows. It also breaks down quickly in sunlight and air, which means you only see plenty of it when something keeps making more. Finding methane on K218b suggests active chemistry, perhaps biological, at a scale that does not fade away. In a hydrogen-rich sky, methane also plays a part in the planet's carbon cycle, the paths by which carbon moves among air, ocean, and life. It can help shape temperature and cloud cover. In that world, organisms might even use methane as a breath of energy, building their bodies in ways that would not work here. The pressure high above the surface brings scenes that, to us, feel magical. At certain heights, carbon atoms are squeezed just enough to snap into the tight, hard pattern we call diamond. These crystals can grow as tiny specks and drift downward like snow. To any creature evolved there, diamond rain might be as ordinary as drizzle, a regular part of the weather. Carbon dioxide adds its own layer of complexity. On Earth, it is a trace gas that plants use for photosynthesis, the process that turns light into food. In a hydrogen-heavy sky mixed with methane and carbon dioxide, new routes for light-driven chemistry can open up. The same sunlight, the same basic atoms, but a different recipe. Life may have learned to harvest energy with pigments and pathways unknown to us, tuned to the glow of a red dwarf star and the soft warmth of a thick atmosphere. The planet turns with one face, always toward its star. One side sees endless day, the other, endless night. This locked dance could create harsh extremes, but the hydrogen blanket smooths them out. Heat moves in great loops from day to night. Moisture and gases ride winds that circle the globe. The result is a constant mixing that keeps the chemistry uniform, the temperatures even, and the chances for life steady across wide reaches on the bright side, at the grey edge of the terminator line, and even in the long dark. A dense atmosphere does more than warm and mix. It protects. Red dwarf stars can flare, throwing out bursts of radiation on a bare world that can strip air and scorch surfaces. On K218b, thick hydrogen absorbs and scatters much of that energy before it can do harm. Layers of gas act like a shield, turning dangerous bursts into softer heat. That buffer may be crucial. It gives fragile molecules time to form. It gives growing ecosystems the chance to pass stress along and recover instead of collapsing. When you put these pieces together, the ocean that stores and shares hydrogen, the air that cycles carbon and spreads warmth, the gentle pressure profile, the global winds you get, a place where life could be both hardy and subtle. It could hide in plain sight, using fuels we rarely see on Earth, refusing to leave familiar oxygen-heavy fingerprints. Instead, it might speak through other gases, through patterns in methane, through traces like dimethyl sulfide, through the quiet absence of compounds such as ammonia that would linger if nothing were alive to use them up. Picture that ocean again. It may have layers set by depth and chemistry rather than by storms and seasons. Near the top, soft light from a red sun filters through haze, feeding slow photosynthesis adapted to warm, rosy wavelengths. Deeper down, organisms might gather near chemical vents, drawing energy from gradients in hydrogen and carbon compounds. Farther still, pressure-tolerant life could build tough, flexible shells or networks, their walls designed to flex rather than break. Predators and prey might not look like anything we know. They might trade energy, not with oxygen and sugar, but with methane, hydrogen, and other simple molecules. Communities could move like drifting veils, following faint currents that carry food and heat. The ocean's reach could be vast. Hundreds of miles of liquid means immense space for niches to form, merge, and split. In such a volume, evolution has room to play. Traits can arise, fade, and reappear in new combinations. Long stability gives time for cooperative webs to grow, where the waste of one species becomes the food of another, and the whole network shapes the air above it. Over ages, that shared metabolism could leave a clear mark in the sky. Steady methane, the right balance of carbon dioxide, the signature of sulfur compounds, and the missing gases that chemistry alone would leave behind. None of this requires a mirror of Earth. It asks only for energy, liquid, and cycles that renew. K218b seems to have all three, and in generous measure, its red dwarf provides a gentle, long-lasting glow. Its hydrogen envelope keeps heat where it is needed and shields the surface from harm. Its ocean stores what the sky spends and gives it back again. In a universe filled with ice worlds and fire worlds, that kind of balance is rare. Where it appears, life can take root and plan for the long haul. So the picture that forms is quiet but bold, a planet with a blended ocean and a protecting sky. weather that moves heat like slow tides, chemistry that writes in new alphabets, yet still tells the same old story of growth, waste, and renewal. Diamonds that fall like snow and mean nothing more than rain does to us. Methane that does not fade because someone keeps making it. Signals, not single, but many some we can read now. Others we will learn to hear as our tools and ideas get better. The more we look, the more this world teaches us to widen our sense of home. Habitability is not a narrow lane crowded with Earth lookalikes. It may be a broad plain that includes hydrogen seas and red suns and air thick enough to shape light. If K218b is any guide, the universe's best harbors for life may not resemble our own shores at all. And that is a gentle, hopeful thought, that life finds a way in places we once thought too strange, and that those places may be kinder than we ever dared to imagine. We are not only finding life on another world, we are finding life inside a new universe of possibility. The star called K2-18 is not a blazing sun like ours. It's smaller, cooler, dimmer, a red dwarf. Yet, this quiet little star might be the most important kind of star in the cosmos when it comes to nurturing life. Red dwarfs burn their fuel slowly, so slowly that their light can last for trillions of years. Our own sun, magnificent but short-lived, will one day swell into a red giant and burn away everything we know. K2-18, by contrast, will glow steadily long after the Milky Way has changed beyond recognition. It offers time on a scale that makes even eternity feel patient. Nearly 3/4 of all stars are red dwarfs. They are the faint, steady heartbeats of the galaxy, small in size, yet countless in number. Most are less than half the mass of our sun, their nuclear fires low and slow. That slowness is a gift. While the sun's lifespan is about 10 billion years, a red dwarf can shine for 10 trillion. Imagine a candle that burns coolly for 1,000,000 nights. That is the rhythm of a red dwarf. For life, time means everything. On Earth, it took almost 4 billion years for simple cells to grow into forests, whales, and us. If a world around a red dwarf has even a fraction of that vast time ahead of it, its living web might already have reached levels of intricacy we can scarcely imagine. Creatures evolved over eons, ecosystems tuned to the rhythm of their calm, steady star. Not all red dwarfs are gentle. Many flare with sudden violence, throwing out bursts of radiation powerful enough to strip air from planets and sterilize surfaces. But K2-18 seems to be a mild one, a star astronomers call well-behaved. It hums rather than shouts. That quiet temperament may have allowed its planets to hold onto their atmospheres, to keep their oceans stable, and to give life a long, peaceful stretch of time to unfold. Despite being smaller and cooler than our sun, K2-18 manages to give its planet, K2-18b, just the right amount of warmth. The planet circles close, finishing one orbit in about 33 days. Its year passes in a month of hours. Yet, because the star is so gentle, that closeness places the planet in the perfect zone for liquid water. Scientists sometimes call it the Goldilocks zone. Not too hot, not too cold, just right. On Earth, this delicate balance has lasted billions of years. Around K2-18, it could last trillions. The window for life there might be almost endless. The two bodies are linked by gravity in a slow dance that has locked one face of the planet toward the star. One side lives in everlasting day, the other in perpetual night. At first glance, this might seem hostile, scorching heat on one side, frozen cold on the other. But K218b's thick atmosphere softens those extremes, carrying warmth across the planet until both halves settle into a quiet, livable calm. It's easy to imagine two different worlds sharing one globe, a bright hemisphere of glowing skies and clouds of diamond dust, and a shadowed hemisphere bathed in the dim reflections of its partner's light. Together, they make a single, stable home. K2-18 itself stands as a kind of promise, a star that won't betray its worlds. Its slow, steady shine is a gift to any creatures living nearby. It means seasons that change little, climates that drift gently, and enough time for evolution to explore every possibility. While our sun's life is a bright, short story, a red dwarf's is an epic poem told across cosmic ages. The distance between us and K218b is vast, yet strangely intimate, about 120 light-years. The light we see from it tonight began its journey when Theodore Roosevelt was president, and airplanes were a fragile new dream. That light traveled through the void for over a century, carrying within it faint codes, the fingerprints of molecules, the breath of alien seas. When it finally reached the golden mirrors of the James Webb Space Telescope, it was so weak that the telescope had to gather photons for hours just to capture a single clear signal. Still, those few particles of light are enough to tell us stories of another world's sky. 120 light-years sounds impossible to cross. Even at the speed of our fastest spacecraft, the trip would take more than 2 million years. And yet, on a galactic scale, K218b is practically in our neighborhood. If we could shrink the Milky Way to the size of North America, Earth would be no larger than a grain of sand, and K218b would be another grain only a small town away. Among hundreds of billions of stars, that's remarkably close. Close enough that our telescopes can read the chemistry of its air, trace the outlines of its atmosphere, and even catch signs of life. Light, in this sense, is a messenger from the past. When we analyze the glow from K218b, we are seeing that planet as it was 120 years ago. The dimethyl sulfide molecules that Webb detected were released into the air when humans on Earth were just beginning to light cities with electricity and send their first radio signals into space. Those faint molecules are like whispers from another time, the exhalations of life beneath an alien sun, arriving at our doorstep a century later. That time delay adds a strange poetry to discovery. We are learning not only that life may exist elsewhere, but that we can watch it across time itself. The breath of creatures on K218b, perhaps floating in warm hydrogen oceans, perhaps drifting in its clouds, left their mark long before most of us were born. Every photon Webb collects is a tiny messenger, telling us that, even in the distance, life leaves a light that endures. If we can sense life this clearly from so far away, the scale of that life must be immense. The organisms producing dimethyl sulfide must be abundant enough, active enough, to shape their entire atmosphere. Life there is not hiding in small pockets. It's rewriting the chemistry of a planet. The power to alter air across an entire world suggests a living network, vast and steady, a biosphere that glows faintly across the void. And because K218b lies so near in cosmic terms, it has become one of the best targets for future study. Our next generation of telescopes, like the extremely large telescope with its 100-foot mirror, will be able to separate its starlight and planetary light with even greater precision. They might detect more biosignatures, perhaps gases we have not yet linked to life, or patterns in its weather that reveal seasonal rhythms. Each new lens will turn the faint whisper of K218b into a clearer conversation. The neighborhood that contains K218b is busy. Astronomers call it our local stellar neighborhood, a small pocket of the galaxy holding a few thousand stars. If even one of them hosts life, the odds are that many others do as well. Life may not be a lonely exception, but a common rule, quietly filling the spaces around us. The discovery of a single living planet nearby hints at a galaxy alive with countless others, each carrying its own stories, its own paths of evolution. There is another thought, quiet but stirring. If life thrives on K218b, and if some of it has grown intelligent, then the same 120 years that separate us might have meaning to them too. Our first radio waves, sent into the sky around 1905, are just now washing over their world. While we're listening to their atmospheric whispers, they might be hearing our first broadcasts, faint echoes of human voices, music, or the crackle of Morse code. Across the space between stars, two civilizations could be brushing fingertips through time. So, when we look at K218b, we're not only seeing a distant world, we're seeing a mirror held up to possibility itself. A small, steady star, a planet with a long memory, a living ocean beneath skies of hydrogen and diamond rain, and light our shared language crossing the dark to say, quietly, that we are not alone. The challenge seemed almost absurd at first. How could you possibly photograph a firefly floating beside a searchlight from 1,000 miles away? That, in essence, was what the James Webb Space Telescope had to do to see planets like K218b. The star it orbits is billions of times brighter than the planet itself, flooding the scene with light so fierce that, under ordinary circumstances, the planet would be completely invisible. The solution came from an old trick one borrowed from studying our own Sunday. For decades, solar astronomers have used instruments called coronagraphs to block the sun's glare so they can glimpse its faint outer atmosphere, the shimmering corona. Webb's engineers adapted that same principle to the deep cosmos. But where a simple metal disc once shaded sunlight, Webb uses an exquisitely engineered ballet of mirrors, masks, and algorithms, the most delicate light-blocking system humanity has ever built. The coronagraph works like a miniature eclipse, holding its hand up against the star so the softer glow of nearby worlds can slip through. But it's far more complicated than a simple shadow. Each mask in the system is tuned to cancel out specific patterns of glare, like muting just the high notes of a blinding song so the quiet melody beneath can finally be heard. The tolerances are breathtaking. A single misalignment of a few billionths of a meter less than the width of a virus would smear the image and erase the planet's signal completely. Astronomers measure a coronagraph's power in contrast ratio, how much fainter a planet's light is compared with its stars. For K218b, that ratio is roughly 10 billion to 1. Imagine standing in a stadium during a night game, floodlights blazing, and trying to see the flame of a single candle beside them from across the country. Webb's coronagraph turns that impossible task into something routine, yet blocking the star's light is only half the work. Once the brilliant glare is gone, the telescope still has to deal with optical ghosts called speckles, tiny distortions in the mirror that can masquerade as planets. Here, artificial intelligence becomes a detective, scanning patterns in real time and separating real worlds from reflections. The computer effort is colossal, comparable to analyzing millions of photographs at once to find one familiar face in the crowd. All this depends on Webb's almost otherworldly steadiness. The telescope must hold its aim with a precision measured in milliarc seconds so steady that it's like keeping a laser pointer fixed on a dime placed on the moon. A tremor, a flicker of heat, even a mechanical sigh from the structure itself would blur the picture beyond repair. The coronagraph does more than block light, it shapes it. Using a process called wavefront correction, the system constantly adjusts the path of incoming light waves, nudging and bending them until they form the sharpest possible image. It's as if the telescope is sculpting starlight, coaxing it into focus so that unseen planets emerge from the brightness like faint ghosts made real. This technology marked a turning point. The coronagraph that revealed K218b is only the first generation of what's coming. Future telescopes will use even finer versions, capable of detecting Earth-sized planets around stars like our own Sunday. Each improvement will expand our reach, uncovering worlds that until now were drowned in their star's brilliance. But perhaps the greatest gift of the coronagraph isn't technical at all. It's philosophical. It reminds us that the universe isn't empty. It's simply hidden by its own light, waiting for us to learn how to look. When scientists calculated K218b's mass, they realized they'd stumbled onto something surprising. The planet weighs about 8.5 times as much as Earth, nearly as heavy as Saturn, but it isn't a gas giant. Beneath its clouds, evidence points to vast oceans of liquid water. This discovery overturned long-held assumptions about what kinds of worlds could be habitable. We've always thought of Earth as the just right, size big enough to keep its air, small enough that gravity doesn't crush us. But K218b suggests that being larger might actually be better when it comes to supporting life over long ages. Its strong gravity keeps a tight grip on its atmosphere, preventing it from escaping into space the way Mars lost its own. Even the strongest flares from its parent star can't strip that thick blanket away. That same gravitational strength also protects its water. On Earth, sunlight sometimes tears water vapor apart in the upper atmosphere, allowing hydrogen to slip into space forever, a slow but steady leak. On K218b, gravity seals the cracks. Its oceans can remain deep and full for billions, maybe trillions of years. Water, the great sculptor of life, would never run dry. Inside the planet, the story grows even more intriguing. The tremendous pressure at its core probably prevents an iron heart like Earth's from forming. Instead, K218b may have a central mass of water ice surrounded by hundreds of miles of liquid ocean, a structure more fluid than rocky, a world whose depths dwarf all our seas combined. Every layer could host its own ecosystems, its own versions of biology adapted to warmth, darkness, and pressure. This extra mass also shapes the planet's long-term rhythm. Large worlds cool slowly. Their interiors stay restless and alive long after smaller planets freeze inside. Earth's mantle is still active today, driving volcanoes and earthquakes, but eventually it will quiet. K218b, being much bigger, could stay geologically active for periods beyond the current age of the universe. Its internal heat might fuel a carbon cycle that refreshes the air, maintaining a steady balance between ocean, rock, and atmosphere. On such a world, stability doesn't mean stillness, it means endurance. Astronomers place planets like K218b in a special class called super-Earths, worlds larger than ours but smaller than Neptune. They exist in that sweet middle range where conditions align beautifully. Too small, and a planet can't hold its air. Too big, and it turns into a suffocating gas giant. K218b sits right at the border, massive enough for deep oceans and a dense atmosphere, yet not so heavy that it loses its surface entirely. It may represent the universe's favorite design for long-lasting, life-friendly worlds. The relationship between mass and habitability is more delicate than we once thought. A planet's size determines how well it can hold heat, recycle gases, and shelter its water. A heavy planet keeps warmth deep inside for ages. That warmth, in turn, keeps its oceans liquid and its chemistry active. It also stirs the layers of the interior, driving the slow churn of geology that helps sustain an atmosphere rich in the ingredients life needs. It's humbling to realize that Earth, for all its perfection, might be the fragile sibling in a vast family of sturdier worlds. Our home has a comfortable balance, but a limited lifespan. Its climate will eventually shift beyond what life can endure. Its oceans will fade. Its sun will outgrow it. K2-18b, on the other hand, could remain stable for 10,000 times longer. For any form of life lucky enough to emerge there, time itself would be generous long enough for evolution to experiment endlessly, to build complexity upon complexity until something extraordinary takes shape. This realization changes what we seek. We are no longer chasing Earth's twin, an exact copy of our blue marble. We are searching for its wiser cousin, bigger, calmer, older, and perhaps kinder. A planet that has learned to last. The discovery of K2-18b doesn't just stretch the limits of our instruments, it stretches our imagination. It reminds us that the rules of habitability are broader than we once believed. Somewhere out there, under hydrogen skies, oceans shimmer in the light of quiet red stars, and gravity holds their air with a patient hand. The cosmos may be filled with worlds more generous than our own, each waiting in silence for the moment we learn to see their faint glow through the glare of their suns. Sometimes, what we don't see tells the most powerful story. The James Webb Space Telescope's next great finding didn't come from a bright, glowing signal, but from an absence, a silent space carved into the light. Around a young star named Ce Antliae, Webb noticed a gap in the dust and rock circling it. That gap, like the trace of a hand pressed into soft clay, revealed the presence of a hidden planet, a new world, quietly shaping the architecture of its home system. Debris disks like the one around Ce Antliae are the leftovers of creation's swirling fields of dust, ice, and shattered rock left behind after a star is born. They're the workbenches of the universe, where gravity and time sculpt new worlds out of chaos. Every speck of dust is a potential building block, every collision a step toward a planet. But once a world begins to take form, it starts to clean up after itself. Its gravity sweeps up nearby fragments, carving clean rings in the dust like the grooves of a record. The clearer the gap, the more massive and active the planet that made it. What made Ce Antliae's disk so striking was its view. From Earth, we see it face on, like looking down into a whirlpool, rather than along its edge. That rare angle gives astronomers a panoramic look at its layout. They can see every ripple, every ring of dust, every graceful arc of debris tracing invisible orbits. Webb's instruments revealed 3 bright bands separated by dark lanes gaps where something massive had swept the path clear. When Webb turned its infrared gaze to those dark spaces, it found a faint glow in one of them, a soft, steady light that shouldn't have been there. It wasn't a dust cloud or a reflection. It was a planet. The world, roughly the mass of Saturn, sits perfectly in the predicted gap between the first and second rings. Its discovery matched computer models so precisely that it felt like seeing a ghost made solid. For the first time, astronomers had caught a planet not by its transit or tug, but by the hole it had carved in the cosmic dust. This method, spotting worlds by the marks they leave behind, opens an entirely new way to search for planets. Rather than waiting for a lucky alignment or measuring faint gravitational wobbles, scientists can now look for the fingerprints of planetary formation itself. It's a quiet, indirect approach, but one that reveals not just the presence of worlds, but their role as sculptors. Each planet becomes a craftsman, shaping the very system it inhabits. The planet orbiting CE Antliae appears young, still gathering mass, still wrapped in the dust that once fed its growth. Its temperature, around 120 degrees Fahrenheit, places it in a gentle zone where liquid water might someday shimmer. It may not yet host life, but it could be a world in its infancy, an unfinished melody in the great song of creation. Webb's discovery reminds us that planet-making is not ancient history. It's happening all around us right now. Young stars are still at their workbenches, hammering light and dust into new worlds. Each image of a debris disk is like peeking into a nursery of planets, a reminder that the universe is never done building. We're not only finding finished worlds, we're watching the birth of new ones, still glowing with the warmth of their making. As Webb continued to turn its gaze toward nearby stars, a wider pattern began to unfold, one that reshaped our understanding of the universe's abundance. The discovery of life on K218b, once thought to be an extraordinary exception, became part of something larger. The cosmos, it seemed, was not dotted with a few rare, habitable worlds. It was alive with them. Within a sphere just 200 light-years across, a mere fraction of our galaxy's width, astronomers have now identified over 50 planets showing signs of habitability. Each has its own personality. Some are super-Earths, with deep oceans and thick atmospheres. Others are smaller, rocky worlds that hug their stars in close, steady orbits. Some are wrapped in greenhouse warmth, with skies that keep their seas from freezing. Others are colder, their surfaces icy but their hearts warm, with hidden oceans beneath their crusts that might cradle life below the frozen stillness. The diversity is breathtaking. Imagine a world where daylight never fades, where the star burns red and low, casting long shadows across an ocean of hydrogen mist, or another where the sky is pale gold, its clouds heavy with methane rain that feeds alien chemistry below. There might be worlds where lightning flickers through ammonia storms, or where crystals of carbon fall as diamonds into seas of liquid water. Each one is an experiment, a different answer to the same question. How does life begin? Different stars write different versions of that answer. Red dwarfs, which make up 3/4 of all stars in the galaxy, burn with slow patience. Their habitable zones are small, but they endure for trillions of years, long enough for life to not only arise, but to thrive, evolve, and diversify beyond anything we can imagine. By contrast, larger, hotter stars live fast and die young. Their planets must race against time, evolving quickly in the brief window before their suns fade. Life there, if it appears, would need to adapt rapidly, a burst of creativity before the lights go out. If 50 promising worlds exist within just 200 light-years, then across our galaxy of 400 billion stars, there could be billions of habitable planets. The numbers defy comprehension. For every person on Earth, there may be several living worlds circling distant suns. The Milky Way could be less a vast emptiness and more a garden, dense with invisible blossoms, ecosystems blooming quietly, unseen. Each of these worlds may have followed its own path, Some might have built atmospheres rich in oxygen, where forests or algae-like forms exhale into the air. Others might breathe hydrogen or methane instead, their biology unrecognizable, but just as alive. Some might have evolved beneath oceans, never seeing their stars. Others might live on land, beneath soft red suns. And a few may host forms of life we have no framework to imagine, systems that don't fit any chemistry we know, yet still pulse with energy, pattern, and persistence. The implications for intelligent life are staggering. If living planets are this common, then minds may be too. Civilizations might rise under every kind of star, some technological, some silent, some still primitive, some already ancient. Our radio telescopes, scanning the quiet sky for a signal, might not need to search for long. Perhaps the reason we haven't heard anything yet is not that no one's speaking, but that we've only just learned how to listen. It's possible that, even now, our oldest transmissions, the faint hum of early radio, the echo of music broadcast a century ago, are brushing against other worlds, reaching alien shores. Somewhere, under a foreign sky, an intelligent species might be detecting a whisper from Earth, the faint memory of a human voice carried across the dark. As Webb continues to map this expanding web of habitable worlds, a larger truth begins to take shape. Life, it seems, may not be a rare accident. It may be as natural as starlight, a process that unfolds wherever conditions are right. When matter cools and energy flows, when oceans shimmer and gravity holds things together long enough, life appears to find a way. Perhaps the universe doesn't simply allow life. Perhaps it expects it. Just as gravity shapes stars and orbits carve rings, maybe biology is another cosmic pattern, written into the laws of existence. That thought changes everything. It turns the night sky from a silent emptiness into a vast neighborhood of potential kin. Each point of light could be a home, not just of matter and fire, but of breath, chemistry, and curiosity. The galaxies might be less a void and more a chorus, each world adding its own note to a universal song of being. We are only beginning to listen to that song, to separate its faint voices from the cosmic noise, the gaps in the dust around distant stars, the flicker of light in the darkness, the quiet spectra of alien air. All of them are pieces of a single truth emerging slowly into view. The universe is alive, not metaphorically, but literally, full of oceans, clouds, cells, and motion, full of beginnings that have no end. We are not on the outside looking in. We are part of it, one small world among billions, each born from the same dust, each warmed by the same kind of star, each carrying the same question: what else is out there? Looking back. Water is the quiet architect of life. It dissolves, connects, and shapes the gentle medium where chemistry turns into biology. On Earth, it forms rivers, clouds, and seas. It carries heat and memory. It writes the story of every living cell. But the water on K218b is something else entirely. It's not a familiar ocean or a passing rain. It's an ocean so vast that Earth's entire hydrosphere would vanish inside it without leaving a ripple. Beneath that world's hydrogen sky lies a body of liquid stretching for hundreds of miles in depth, perhaps thousands, the largest known sea of its kind anywhere beyond our solar system. The first hint came from the faintest of signals, a few missing colors in the starlight that reached the James Webb Space Telescope. Those gaps, carved by molecules absorbing certain wavelengths of infrared light, told astronomers what the planet's atmosphere was made of. Among those signatures was a pattern unmistakably shaped by water vapor. It was not a trace or a thin mist. It was abundant, woven through the air from top to bottom. That much vapor could exist only if enormous oceans below were feeding it continuously into the sky. On Earth, our oceans hold about 350 million cubic miles of water. They cover most of the planet's surface, but their average depth is only a few miles, a thin glaze of blue across a rocky sphere. On K218b, the water could be 1,000 times more plentiful. Picture an entire planet wrapped in a global ocean. No continents to break it, no dry land anywhere. From the stars' reflected light, there might be nothing but shimmering blue, stretching from pole to pole. Down below, the pressure would build into unimaginable weights, strong enough to crush any submarine we could send. Yet this enormous sea isn't made of ordinary water alone. Mixed within it is the hydrogen that fills the planet's thick atmosphere, forming a liquid unlike any found on Earth. Hydrogen and water together create a kind of solvent that stays stable across an immense range of temperatures and pressures. Where our oceans would freeze or boil, these waters remain fluid. They can exist near the edge of ice or under the heat of 300 degrees Fahrenheit without breaking apart. It's as though K218b's chemistry has widened the safe zone for life, turning extremes into comfort. Such water could feed strange metabolisms. On Earth, a few rare microbes can breathe hydrogen, drawing energy from it the way we use oxygen. But on K218b, that resource would be everywhere, dissolved into the sea itself. Life there might not breathe air at all. It might breathe the ocean. Every bubble could hold energy, every current a flow of food. Instead of sunlight alone powering ecosystems, chemical gradients between hydrogen and carbon compounds might sustain entire webs of life. The stability of this ocean might be its most extraordinary gift. Here on Earth, water slowly escapes us. High in our atmosphere, sunlight breaks some of it apart, letting the light hydrogen drift away forever. Over deep time, our seas will shrink, our clouds will fade. But on K218b, the planet's strong gravity and thick atmospheric blanket keep its water bound. Even when hydrogen is lost to space, more rises from the ocean to replace it. This feedback could hold steady for trillions of years, long enough for life to not just emerge, but to endure, adapt, and flourish across epochs beyond imagination. The temperature of those oceans, measured at roughly 120 degrees Fahrenheit, sits in a sweet spot for biology. Warm enough for chemistry to happen quickly, cool enough to protect complex molecules from breaking apart. On Earth, that same temperature would feel like a hot spring, gentle, not hostile. It's easy to picture a world bathed in steam and soft light, an entire planet poised at the perfect heat for life to thrive. Water doesn't just nurture life, it shapes climate. On K218b, the oceans likely act as a vast regulator, absorbing carbon dioxide from the air and releasing it again as needed, keeping the temperature steady. On Earth, the same carbon cycle has held our planet within a narrow range of habitability for billions of years. On K218b, that balance may be even more precise, tuned by an ocean 1,000 times larger, a thermostat so stable that complex ecosystems could evolve without fear of collapse. And if K218b is typical of super-Earths, it may only be one among countless others. The galaxy could be strewn with these vast blue worlds, oceanic planets, orbiting quietly around dim red suns, each carrying water in quantities beyond imagination. The discovery doesn't just tell us that water is common. It tells us that ocean worlds themselves may be the rule, not the exception. the universe may not just hold scattered drops of life, but entire seas of it. Every molecule of that water carries a story, told in light. When a planet passes in front of its star, some starlight filters through its air before reaching us. Each gas leaves its mark, a missing line here, a subtle dip there. Astronomers call this a transmission spectrum, a cosmic fingerprint that reveals the planet's chemistry. It's a method as delicate as reading an ancient manuscript from across space, tracing invisible ink with beams of infrared light. When Webb analyzed K218b's spectral fingerprint, it found something that defied the quiet logic of lifeless chemistry. The mixture of gases in the atmosphere didn't make sense for an inert world. In a dead system, elements find balance, reactions settle, and the atmosphere reaches equilibrium, changing only with time or disaster. But K218b's skies were restless. They contained molecules that should have destroyed each other long ago: methane alongside carbon dioxide, traces of water, and, most surprisingly, dimethyl sulfide, a compound that on Earth is made only by living cells. This chemical chaos is what scientists call disequilibrium, the telltale breath of life. Our own atmosphere shows the same pattern. Oxygen and methane coexist, even though they should react away, because living things keep replenishing them. On K218b, a similar imbalance hints at the same process. Something there is continually producing gases, fighting against the steady pull of chemistry toward calm. The presence of dimethyl sulfide makes this conclusion even stronger. The molecule breaks down quickly when exposed to light and air. If it exists in measurable quantities, something must be making more all the time. And it's not confined to one place. The data show it spread throughout the atmosphere, suggesting that whatever life produces it isn't isolated to small pockets, but is widespread, possibly global. A living planet, breathing from ocean to sky. The fingerprints also reveal hints about what that life might be like. With hydrogen and methane dominating the atmosphere, organisms there could use them as energy sources, metabolizing in ways completely foreign to us. On Earth, such reactions happen only in small, extreme niches, deep ocean vents, underground pockets, or specialized microbes. On K218b, those same processes might define an entire biosphere. Life could be built from pathways we've never studied, thriving in chemistry that looks alien, but follows the same universal rule: find energy, use it, survive. Detecting these signals requires astonishing precision. Webb must measure changes in starlight intensity at the level of 1 part in a million, as if trying to detect the weight of a single snowflake on a mountain. It must separate the planet's faint glow from the overwhelming light of its star, and then read the spectrum, line by line, molecule by molecule. Each piece of data is fragile, but together they form a story written in physics, chemistry, and time. What that story tells us is more than just the presence of life. It speaks of a world where life changes its surroundings, where biology reshapes atmosphere and ocean alike, creating feedbacks that keep the planet alive. On Earth, we call that the biosphere, the thin layer of air, sea, and soil that all living things maintain together. On K218b, the biosphere might stretch from the top of the clouds down through hundreds of miles of liquid water, a continuous living sea under a hydrogen sky. This discovery doesn't only expand our map of possible habitats, it changes the way we think about life itself. It reminds us that biology is not fragile. It adapts to gravity, pressure, chemistry, and time. It learns to use what's available to breathe hydrogen, to live in water that would crush our bones, to balance its world for as long as its star will shine. In the faint light from K218b, across more than 100 light-years of empty space, we see a reflection of our own story, the chemistry of a world that learned to breathe, to build, to sustain itself. Each dark line in the planet's spectrum is a sentence written by its living oceans, a quiet message carried across the dark. We are here too. The day humanity first reads that message clearly, when the fingerprints of life become unmistakable, will not be the day we discover something alien. It will be the day we recognize a pattern that feels deeply familiar. The pattern of matter coming alive, again and again, wherever the conditions are kind. And K218b, with its vast hydrogen oceans and warm, patient seas, may be the universe's most eloquent example of that ancient truth, that life does not wait for perfect conditions, it builds them. The star called CE Antliae is a child of the galaxy only about 6 million years old, still wrapped in the dusty remains of its own birth. Around it swirls a glowing halo of rock, ice, and vapor, a debris disk, the after-image of creation. Within that disk, planets are taking shape, growing grain by grain, orbit by orbit. This is what astronomers call a cosmic nursery, a place where chaos and structure coexist, where gravity sculpts and light hardens matter into worlds. Youth in the cosmos is not gentle. Young stars like CE Antliae are restless and erratic, pulsing with tantrums of light and heat. They flare suddenly, pouring out bursts of radiation thousands of times brighter than their steady glow. Each flare sends waves of energy crashing through the surrounding dust, sterilizing some regions and igniting others. For any planet nearby, it is both a trial and a gift. The same violence that could strip away an atmosphere might also fuel the chemistry that leads to life. The planet that Webb found within this storm, glowing faintly at a comfortable 120 degrees Fahrenheit, seems to have weathered the fury well. It orbits in a gap between rings of debris, a space it carved for itself, and somehow it endures the star's rages while basking in its warmth. Its survival speaks to balance, to resilience. Life, if it ever stirs there, would be born knowing how to endure extremes. The disk surrounding CE Antliae is a living diagram of planetary formation. The innermost ring is a haze of fine dust and stone fragments, the first building blocks of future worlds. The middle ring, where the new planet orbits, holds larger bodies, boulders of ice and rock drawn together by their own gravity, swept clean where the planet has gathered them up. The outer ring remains untouched, pristine, a record of what the system once was before planets began to assemble. Each ring tells a story of time and motion. The young planet, still hungry, collects debris as it moves, gaining mass with every orbit. When fragments collide at high speed, they melt, compress, and reform into more complex materials. These violent mergers may seem destructive, yet they create the heat and pressure that spark intricate chemical reactions. Simple elements fuse into compounds, and compounds into organic molecules, the seeds from which biology can eventually grow. The star itself contributes to this alchemy. Its fierce ultraviolet light splits apart simple molecules in the planet's forming atmosphere, producing unstable fragments that race to recombine in new ways. It's a natural chemistry lab on a planetary scale, mixing carbon, nitrogen, and hydrogen into ever more elaborate patterns. Over time, these reactions could fill the air and sea with the precursors of life: amino acids, hydrocarbons, and other building blocks waiting for the right spark. Meanwhile, the planet's gravity acts like a sculptor's hand, shaping the debris around it. It clears its own orbit while sweeping nearby material into smooth, organized lanes. The result is not chaos, but rhythm, a gravitational dance where matter moves in step, forming rings and gaps as precise as the grooves on a record. Each orbit leaves its mark, and the whole disk becomes a portrait of balance emerging from disorder. This interaction between planet and disk forms a self-sustaining loop. As the planet grows, its pull strengthens, which clears more space, which brings more material into its path. Each collision, each flare, each new layer of atmosphere feeds into the next stage of formation. In this way, a young world and its star co-create one another's story. The star providing energy, the planet shaping structure, both locked in a partnership that may last for billions of years. The discovery of a warm, possibly habitable world in such a raw environment challenges long-held beliefs about when and where life can begin. For decades, scientists assumed that life needed quiet, stable climates, old stars, long ages of calm. But C.E. Antlier's planet suggests something different. It hints that life might not wait for peace. It might arise amid turbulence, forged by radiation and collision, thriving on the very forces that seem hostile to it. To understand how this planet was found, it helps to look closer at its home. The debris disk around C.E. Antlier contains a mystery, a perfect gap that spans millions of miles between the first and second rings. According to the rules of physics, that space should be full of dust and rock fragments, yet it is almost completely clear, as though something enormous has swept the path clean. For years, astronomers puzzled over this emptiness. Ground-based telescopes showed the shape of the disk but not the cause of its gaps. Magnetic fields could not explain it, nor could random collisions. Only gravity steady, massive, invisible could clear such a channel. But the source remained hidden, lost in the glare of the star. Then the James Webb Space Telescope turned its infrared eyes toward the system. Its sensors, tuned to the faint glow of warmth rather than visible light, pierced the veil of dust and revealed a subtle beacon, a soft, steady heat signature inside the gap. There it was, a young planet, roughly the size of Saturn, circling its star and sculpting its surroundings. Its orbit lay exactly where computer models predicted, the missing piece in the puzzle of C.E. Antlier's rings. What makes this discovery so remarkable is the precision of the gap itself. Planet formation theory suggests that young planets clear channels as they grow, but the one around C.E. Antlier's world is nearly perfect. Its edges sharp, its interior almost entirely empty. That clarity implies time and stability. The planet has likely been circling there for millions of years, long enough to organize its neighborhood into orderly layers. This finding reshapes how scientists think about planetary growth. It suggests that even in systems only a few million years old, planets can mature quickly enough to influence their entire environment. The debris disk becomes not a chaotic storm, but an ecosystem in motion, where every grain of dust knows its place in a larger pattern. Computer simulations of the C.E. Antlier system show how this works. The planet's gravity creates resonant zones, pockets of stability, where debris can orbit safely without being pulled in or flung away. These safe havens correspond exactly to the bright rings that Webb observed. In essence, the planet acts as a cosmic architect, laying out the blueprint of its own solar system. The gaps are the hallways, the rings, the walls. The materials that the planet gathers tell their own story. Many are rich in water, ice, and volatile compounds, frozen carbon dioxide, methane, ammonia. As the planet absorbs them, they melt and mix into its atmosphere, adding the elements needed for weather, for oceans, for chemistry that might someday support life. The current surface temperature of about 120 degrees Fahrenheit suggests a world warm enough for liquid water, wrapped in an atmosphere thick enough to hold it. The gap itself becomes more than an absence. It's evidence of organization, of gravity and time cooperating to build structure out of dust. In that sense, the planet's empty orbit is like a footprint pressed into the soft dust of creation, a sign that something solid, lasting, and alive in its motion has passed through. If we could see this system up close, it might look like a glowing clockwork of light and shadow, rings of glittering particles turning slowly, a dim red star pulsing at the center, and in one wide, clean band, a planet tracing its endless path, herding stray fragments into line. The quiet order of those rings stands as a kind of promise. Even in chaos, there is pattern. Even in violence, there is the potential for life. C.E. Antlier reminds us that creation is rarely calm. Worlds are born amid heat, pressure, and the shock of impact. But from that turmoil comes stability, and from that stability, the possibility of life. The planet in this young system may still be gathering its final layers, still shaping its air and water. Its story has only just begun, but already it has rewritten part of ours. For every system like C.E. Antlier scattered across the galaxy, countless others are following the same script, stars flaring and fading, disks spinning and settling, planets clearing their paths. Each gap in a ring of dust may mark the start of something extraordinary, a new world learning to exist. And perhaps somewhere deep in the future, when the star has quieted and the planet's surface has cooled, that same energy that once tore molecules apart will have built them up again into cells, into patterns, into life. The flares that once seemed deadly will be remembered as the sparks that lit the first fires of biology. The debris disk's perfect gap is not merely an empty space in the cosmos. It is a message in light and shadow, telling us that even the youngest, wildest corners of the universe are busy creating structure, preparing for life's arrival. C. Antlier's planet shows that order doesn't wait for peace. It emerges from the storm. In the glowing dust of that red dwarf, we see the story of beginnings repeating itself. Worlds born from fire, carving their paths toward calm, carrying the potential for life wherever light and gravity meet. Across the vast silence of space, one number keeps whispering its way back to us: 120 degrees Fahrenheit. It appears again and again in the data, in the atmospheres of distant worlds, in the oceans of super-Earths, even in the warm glows that circle young stars. It's as if the universe, in its grand experiment with life, has found a favorite temperature, a point of balance between order and motion, between chemistry and creation. At this warmth, water doesn't freeze or boil. It flows, dissolves, mixes, and carries. Molecules that would lie dormant in cold become restless here. They collide, react, and rearrange themselves into the beginnings of something intricate. This is the middle ground where physics gives way to biology. At 120 degrees Fahrenheit, water reveals its genius. It's liquid enough to dissolve almost anything that life might need: salts, gases, minerals, carbon compounds, and it transports them with perfect efficiency. It's warm enough to speed up reactions, letting metabolism hum at a steady rhythm, yet gentle enough not to tear complex molecules apart. It's a natural incubator, a universal setting that seems almost tuned for life. to build itself piece by piece. What makes this even more intriguing is that we've seen this temperature before, not on other planets, but deep beneath our own oceans, around the vents that crack the seafloor, where darkness reigns and sunlight never touches. Water heated to roughly this same temperature gushes from Earth's interior. There, in that alien darkness, life thrives. Not plants or animals as we know them, but microorganisms that breathe chemicals instead of air, that feed on minerals instead of sunlight. These creatures, ancient and resilient, may be Earth's oldest forms of life. The resemblance is striking. On faraway worlds where light is dim and warmth comes from within, conditions mirror these deep-sea vents. Life there might not depend on sunlight either. It could rely on chemistry alone. Such chemosynthetic life might breathe hydrogen or methane, drawing energy from the same kinds of reactions that power volcanoes and hot springs here. Laboratory experiments support this idea. When scientists recreate the temperatures and pressures around 120 degrees Fahrenheit, amino acids, the tiny building blocks of proteins, form readily. At lower temperatures, the reactions crawl. At higher ones, the fragile molecules fall apart. But in that middle range, life's chemistry flourishes. It's as if this temperature is not random, but written into the logic of matter itself, a thermal sweet spot where nature becomes creative. Different worlds reach that balance in different ways. Some trap heat with thick blankets of gas, their atmospheres acting like gentle greenhouses. Hydrogen, carbon dioxide, and water vapor all hold warmth, keeping the surface cozy even when their suns are faint. Others are heated from within, their cores still alive with radioactive decay or tidal forces that squeeze and warm them. A few use both, star above and heat below, combining to create an enduring equilibrium. And across all these systems, the number repeats. Time after time, Webb's instruments have read that familiar thermal note, 120 degrees Fahrenheit. It's too consistent to ignore. The same way stars fall naturally into certain sizes and brightness levels, perhaps planets do too. Maybe there's a universal comfort zone, a preferred range where biology can bloom. The implications are immense. A stable warmth like this doesn't just allow life, it encourages it. Chemical reactions run faster, mutations occur more frequently, evolution gains momentum. Life on such worlds might adapt rapidly, exploring endless variations while still enjoying stable climates that prevent extinction. A biosphere in this perfect warmth might grow more quickly and diversely than ours ever could. Some scientists are beginning to wonder if this recurring temperature is a kind of cosmic signature, a subtle hint that life doesn't merely happen by accident, but follows natural laws we're only beginning to glimpse. Perhaps the universe itself is structured in such a way that life is not rare, but inevitable, expressing itself wherever matter finds the right warmth, the right chemistry, the right rhythm. And then, in that same golden range of temperature, another clue glows in the spectrum of K218b methane. A simple molecule, one carbon surrounded by 4 hydrogens, yet it's causing scientists to reconsider everything they know about that distant world. Methane should not last long in an atmosphere flooded with ultraviolet light. It reacts quickly, breaking apart under radiation. On a lifeless planet, it would vanish in short order. Yet, on K218b, Webb has found it in abundance, far more than any geological or chemical process could explain. On Earth, methane is one of life's most familiar exhausts. It bubbles from swamps where bacteria feed on decaying matter. It seeps from the stomachs of grazing animals and the roots of certain plants. Wherever organic life breaks down and rebuilds, Methane is part of the cycle, and almost every known source of it here is biological. So what does it mean when we find methane swirling through a hydrogen-rich atmosphere 120 light-years away? It means something is keeping that gas replenished, producing it faster than it can be destroyed. Something alive. But this methane mystery goes beyond simple presence. It points to an entire alternative ecosystem. In a world where hydrogen dominates the air, methane could play the role that oxygen does on Earth. Instead of breathing oxygen and exhaling carbon dioxide, life there might inhale methane and exhale something entirely new. Its metabolisms could be chemical mirrors of our own, running on different fuels, but guided by the same fundamental drive: to use energy, to grow, to persist. Inside K218b's atmosphere, methane doesn't exist alone. It dances with hydrogen, carbon dioxide, and traces of dimethyl sulfide, forming a chemistry of immense richness. Under those conditions, laboratory experiments show that new organic compounds can emerge spontaneously: amino acids, complex hydrocarbons, even precursors to lipids. It's a chemistry workshop as large as a planet, mixing and remaking itself continuously. The sheer amount of methane Webb detected suggests that whatever is producing it operates on a planetary scale. This isn't the output of a few microbes eking out an existence in hidden pools. It's the breath of a biosphere, a living world that has reached equilibrium with its environment, transforming it from the inside out. Even more astonishing is what this implies about time. For such a steady chemical balance to exist, life must have been active for ages, millions, maybe billions of years, long enough for the planet's atmosphere and climate to stabilize around it. This would make K218b not a newly awakened world, but an ancient one, where life has already matured into a global force. The variety of gases also suggests diversity among the organisms that produce them. Different species could be using different chemical pathways, some generating methane, others consuming it, some using hydrogen directly, others forming complex organics from carbon dioxide. Instead of forests and oceans, K218b might have layers of life stacked vertically through its atmosphere, each zone home to distinct metabolisms adapted to temperature, pressure, and light. This layered ecosystem would make the atmosphere itself an ocean of life, waves of gas and chemistry sustaining billions of microscopic forms. The entire planet could function like a single living organism, its air breathing, its oceans exhaling, its clouds pulsing with cycles of growth and decay. To call this just a chemical puzzle would be to miss the point. The methane on K218b is a sign of motion, not just physical, but biological. It's the rhythm of metabolism scaled up to a planetary heartbeat. It suggests that somewhere out there, life has learned new ways to thrive, using the simplest of molecules to build complexity far beyond what we've imagined. Perhaps that's what 120 degrees Fahrenheit really signifies. Not a coincidence of climate, but a universal rhythm. The temperature where molecules dance most gracefully, where reactions balance between chaos and structure, where the line between chemistry and life becomes beautifully blurred. And so the data from Webb, these delicate traces of light crossing the abyss, speak of something both familiar and foreign, a cosmos that seems to prefer life, to favor warmth, to repeat certain harmonies wherever the conditions allow. The more we look, the clearer the pattern becomes: water and warmth, hydrogen and methane, and always that same perfect heat. Somewhere out there, under a sky that glows faintly red, oceans are steaming softly, and invisible organisms drift through the air, feeding on gases, exhaling new ones, shaping the weather of an entire world. They are living proof that the universe is not indifferent. It creates, again and again, the same chemistry of wonder and perhaps the same miracle of being alive. The discoveries made by the James Webb Space Telescope from the oceans of K218b to the hidden planets circling CE Antlier mark the opening chapter of a new era in exploration. For the first time, humanity has learned not only to detect light from distant worlds, but to read that light for signs of life. Each observation, each pattern in the data, whispers that biology leaves fingerprints even across the void. And now, astronomers are preparing to listen more carefully than ever before. This next great endeavor is called the Biosignature Survey, a systematic, decade-long effort to search hundreds of nearby star systems for the chemical hints of life. Over 200 suns, all within 100 light-years of Earth, will become targets. Every potentially habitable planet orbiting them will have its atmosphere examined in exquisite detail. The goal is simple but profound: to map life across the galaxy, one spectrum at a time. Webb, already the most sensitive observatory ever built, will stretch its capabilities even further. New observing modes will allow it to study worlds that never pass directly in front of their stars, planets that, until now, were invisible to our instruments. Instead of waiting for shadows, scientists will search for subtler signatures, faint glimmers of reflected light, shifts in infrared color that betray the breath of living chemistry. Artificial intelligence will be a key partner in this survey. Advanced algorithms are being trained to sift through oceans of data, looking for complex molecular patterns, not just water and methane, but combinations of gases that point to metabolism, weather cycles, even the byproducts of entirely alien biologies. These systems will look for patterns that humans might miss, subtle rhythms of chemical imbalance, atmospheres that behave as though something beneath the clouds is alive and responding. The survey will also add a new dimension: time. Life, after all, is not static. On Earth, our atmosphere changes with the seasons, pulsing with the cycle of growth and decay. The amount of oxygen and carbon dioxide shifts as plants awaken and rest, as oceans breathe and exhale. Astronomers plan to watch exoplanets in a similar way, revisiting them over months and years to see if their atmospheres change. A planet whose chemistry fluctuates with regularity might not just host life, it might host ecosystems in motion. And beyond biological life, there's another kind of signature the telescope will seek: technosignatures, the chemical and optical fingerprints of technology itself. Industrial processes, if they exist elsewhere, would release gases unlike those made by nature. Artificial compounds like chlorofluorocarbons or nitrogen oxides could persist in a planet's atmosphere, visible across light years. Detecting them would mean something extraordinary, not just living organisms, but intelligent beings shaping their environment as we do. Other telescopes will join this cosmic collaboration. Radio observatories will listen for deliberate transmissions from stars where Webb finds biological clues. Optical telescopes on Earth will search for glints of artificial lighting, faint city-like glows on the night sides of alien worlds. Together, these instruments form a network, a web of watchers spanning light, sound, and time. For the first time, humanity will conduct a complete census of its cosmic neighborhood. Meanwhile, new technologies are already being prepared. Improved coronagraphs devices that block out starlight to reveal orbiting planets will let Webb and its successors study smaller, Earth-sized worlds directly. Future spectrographs will split starlight into even finer detail, revealing not just what gases exist, but how they move and interact. Machine learning models will learn to extract meaning from noise, finding signals too faint for traditional analysis. In a sense, this is humanity's first true map of life. If the first explorers charted coastlines and mountains, we're now charting biology itself, invisible, but no less real. Within a decade, the data may reveal hundreds of worlds with distinct chemical signatures, each representing a different version of the same story, matter becoming alive. For the first time, we'll be able to trace life's distribution through the Milky Way, from one faint point of light to the next. It's an astonishing thought that within our lifetimes, we may come to see the galaxy not as a wilderness, but as a community of living worlds. Each will have its own rhythm, its own history, its own chemistry. Some may be young, still stormy and raw like C.E. Antley's planet. Others may be ancient, their biospheres matured into stable balance. The question, are we alone, is slowly losing its urgency. The answer, whispered in infrared light, appears to be no. We are surrounded by company we've only just begun to recognize. While Webb prepares to search for living skies, it has already shown us what birth looks like, not of life, but of planets. The debris disk around C.E. Antley resembles a grand three-ring structure suspended in space, each band telling a different part of a cosmic story. From afar, it looks like a sculpture made of dust and light, yet within those rings, gravity and chemistry are hard at work, crafting new worlds. The innermost ring, nestled close to the red dwarf star, glows with the heat of molten rock. Temperatures there could melt lead, yet dust grains persist, circling in tight, feverish orbits just a few million miles from their sun. These tiny particles constantly collide and fuse, slowly building the dense seeds that will become the cores of rocky planets. It's the earliest chapter of creation, when dust learns to stick together. Farther out lies the middle ring, a region of balance, where heat softens but does not destroy. Here, rock and ice coexist, forming the raw materials of complex worlds. The planet that Webb discovered moves through this region, clearing its path while pulling in debris to grow. The remaining dust still bears the scars of this process, streaks and eddies left by gravitational tides. It's a portrait of a planet still forming, still feeding, still sculpting its home. Then comes the outer ring, the cold frontier. Its material is pristine, untouched, since the star's birth, a reservoir of frozen water, carbon, and organic compounds. In time, pieces of this distant ring may be nudged inward by gravity or collision, delivering icy cargo to inner worlds. In systems like ours, this is how comets brought water to dry planets, how lifeless rocks became oceans. The outer ring is a vault of possibilities, keeping the ingredients of life preserved in deep cosmic cold. The arrangement of these rings isn't random. It follows the mathematics of orbital mechanics, the quiet logic of gravity. Each ring sits in a region where material can circle stably, while the gaps between them mark zones of resonance where gravity disrupts order. These boundaries are not accidents. They are the fingerprints of the planets shaping them. The gaps are not empty. They are sculpted space, carved by worlds into clean divisions that reveal the invisible architecture of the system. Viewed together, the three rings form a timeline. The inner ring shows the dawn of planet-building small dust becoming larger bodies. The middle ring, home to the new planet, captures the era of active growth. The outer ring represents the waiting future material, still untouched, poised to join the process. Each ring is a moment frozen in time, yet all are linked in motion, feeding one another as the system matures. Computer simulations of CE Antliae's disk reveal this interplay vividly. Material from the outer regions drifts slowly inward, spiraling toward the star. But the newborn planet acts as a guardian, regulating the flow. Its gravity prevents the outer material from collapsing inward too fast, ensuring that the system grows in balance rather than chaos. It's a delicate choreography, a feeding process that allows each layer to evolve at its own pace over millions of years. Seen this way, the disk around CE Antliae isn't just a pretty pattern. It's a universal machine, the same kind of structure that once surrounded our own sun when Earth was forming. Similar rings have been spotted around dozens of young stars. The same mathematics, the same rhythm, repeats across the galaxy. Wherever dust and light meet, gravity draws the same spiral, crafting order from turbulence. In the glow of that red dwarf and the cold shimmer of its rings, we are witnessing a familiar miracle, the universe making worlds again, as it has done countless times before. Each grain of dust is a potential planet, each collision a spark of future chemistry. The three rings of CE Antliae remind us that creation is a process, not an event. The steady turning of time, the slow sculpting of chaos into harmony. As Webb continues its mission studying the skies for living worlds, mapping the light of their atmospheres, decoding the hidden order of dust and stars, it draws us into a larger realization. Life and matter are not separate stories. They are chapters of the same one. From the first dust rings around newborn stars to the green breath of distant planets, the cosmos repeats its patterns. We are not merely observers of that pattern. We are part of it, a species born from dust, warmed by a star, now reaching out to find our kin among the galaxies. In the quiet data streaming back from space, we are beginning to hear the universe's voice. It doesn't shout, it hums, softly but clearly. I am full of life. The discovery of the planet orbiting CE Antliae marks a quiet but historic turning point in the search for other worlds. It's not just another exoplanet, it's a boundary breaker. With a mass only 1/3 that of Jupiter, it is the lightest planet ever directly imaged around another star. For decades, astronomers had dreamed of seeing a world like this, one small enough to resemble the planets in our own solar system, yet distant enough to test the limits of our technology. Now, thanks to the James Webb Space Telescope, that dream has stepped into focus. Until now, direct imaging had been the realm of super Jupiters, huge, blazing hot worlds several times the mass of our own gas giant. They were easy targets because they were bright, their heat making them glow like miniature stars beside their suns. But CE Antliae's newly found planet is different. It's faint, cool, and subtle, 10 times less massive, and 10 times harder to see. Webb had to isolate a whisper of light roughly 10 billion times fainter than the star beside it, a feat that pushes physics to its breaking point. This single detection is both a scientific and an engineering triumph. Imagine trying to spot a single firefly fluttering next to a stadium floodlight from hundreds of miles away through a fog of swirling dust, and then not only seeing it, but studying the faint color of its wings. That's what Webb has done. The telescope's infrared instruments, coronagraph masks, and computer algorithms work together to extract a thread of light that would otherwise drown in the star's brilliance. But the planet itself, quiet and dim though it is, may hold far more significance than its brightness suggests. With a mass at the border between gas giant and rocky world, It sits in the gray zone of planetary formation, the region where worlds may go one way or the other. Too large, and they become Jupiter-like, cloaked forever in clouds of hydrogen and helium. Too small, and they end up rocky, like Earth or Mars. This world sits at the edge of that divide, giving scientists a front-row seat to the moment when nature decides what kind of planet will form. Understanding that boundary helps us understand how habitable planets arise. For a world to nurture life, it must be large enough to hold onto an atmosphere, but not so large that it smothers itself beneath crushing gases. C.E. Antlier's planet, with its relatively modest gravity and a surface temperature of around 120 degrees Fahrenheit, appears to have struck that delicate balance. It likely possesses a solid or liquid core surrounded by a breathable, protective shell of gas, neither too thick nor too thin. Detecting such a subtle object demanded not only Webb's immense mirror, but also new techniques in data cleaning and pattern recognition. The light from the planet had to be disentangled from glare, from scattered dust, from the shimmering noise of starlight itself. Each image was processed through algorithms that removed every trace of contamination until only the faint pulse of infrared warmth remained. It's like filtering thunder to hear a single distant heartbeat. Because of its thin atmosphere, this planet offers scientists something precious: depth. On massive gas giants, thick clouds block our view of lower layers, hiding most of the chemistry that tells us how the planet works. But C.E. Antlier's smaller world allows infrared light to penetrate deeper. Webb can read not just the outer weather, but the chemical fingerprints beneath water vapor, carbon dioxide, methane, and other molecules that hint at geological and perhaps even biological activity. The true importance of this discovery lies in what it proves. For the first time, Webb has shown that it can directly image planets within the same mass range as those orbiting our Sunday. This means the telescope and future missions that will follow can now hunt for Earth-sized worlds using the same methods. We are no longer confined to studying giants. We're inching toward the realm of true analogues to home. In many ways, this faint little planet opens the door to a new golden age of exoplanet science. Its light is a promise that technology has finally caught up with imagination. And what's coming next could change everything. The next 2 decades of astronomy are already taking shape. Plans are underway for the Habitable Worlds Observatory, HWO, a mission designed explicitly to seek out and study Earth-like planets around sun-like stars. Where Webb is a generalist, a cosmic all-rounder, HWO will be a specialist, a precision instrument built for one purpose: to find life. This telescope will use an advanced coronagraph capable of blocking starlight with a contrast ratio of 10 billion to 1, enough to make the faint reflection of a small planet visible against the glare of its sun. It will search not just for hydrogen or carbon dioxide, but for the unmistakable signs of biology: oxygen, water vapor, methane in delicate imbalance, even the complex molecules that hint at photosynthesis or respiration. For the first time, humanity will look at other worlds not as points of light, but as places. On Earth, meanwhile, construction is rising on a different giant: the extremely large telescope in the Atacama Desert of Chile. Its mirror, stretching over 100 feet across, will dwarf every optical telescope that came before. From its mountaintop perch, it will dissect the light of nearby exoplanets, breaking it into thousands of precise colors. Each spectral line will tell a story of gases, temperatures, pressures, and possibly of life. The ELT will be able to identify dozens of molecular species in a single exoplanet's air, painting a detailed portrait of alien weather and chemistry. Artificial intelligence will be the glue that binds this future network of observatories together. The data volume will be staggering petabytes of spectra, images, and time series measurements pouring in daily. Machine learning systems are being trained not only to sort through this flood, but to recognize patterns invisible to human intuition, subtle harmonies of gases, statistical fingerprints of metabolism, atmospheric imbalances that whisper, "Something is breathing here." These systems could one day identify life forms based on chemical logic entirely different from our own. Scientists are also moving beyond traditional biosignatures like oxygen and methane. The next frontier is agnostic biosignatures, chemical clues that point to life regardless of its structure or chemistry. Instead of looking for specific molecules, astronomers will look for atmospheres in disequilibrium mixtures of gases that shouldn't coexist unless something is constantly renewing them. On Earth, that something is life. The same principle could hold anywhere. The technology is evolving so fast that the next generation of instruments may even detect life in real time. Continuous monitoring of exoplanet atmospheres could reveal changes from day to night or season to season, the daily breathing of alien ecosystems. Imagine watching the carbon dioxide levels of another world rise and fall with its day, or seeing methane spikes that track the motion of weather systems alive with microbial storms. And then comes the next question, the one that lingers just beyond biology. Are there civilizations out there? As sensitivity improves, astronomers hope to detect technosignatures, the traces of technology itself. Industrial pollutants, for instance, leave chemical residues that no natural process can mimic. Even the glow of artificial lights, seen from the dark side of a planet, might betray cities beneath alien skies. For the first time, the search for intelligence will no longer be limited to radio waves. It will be written into the light of the stars themselves. If Webb and C.E. Antlier's planet mark the dawn of this age, then the next few decades will be its sunrise. The combined power of HWO, ELT, AI analysis, and a global network of instruments will give humanity what we've never had before: a map of life itself, stretching from our solar neighborhood to the edges of the Milky Way. Every discovery, every faint glimmer of methane, every spectral fingerprint of oxygen adds another point to that map. Soon we may find ourselves surrounded not by empty stars, but by neighbors we can finally recognize. Some will be young worlds just forming, like C.E. Antlier's planet. Others may be ancient, their civilizations already old when our ancestors first lit fires. The lightest planet ever imaged has done more than set a record. It has shown that the universe's story is still unfolding, that our technology has finally reached the sensitivity needed to hear the faintest verses of that cosmic song. With each improvement in our instruments, the silence between stars grows thinner, until one day, perhaps not long from now, we may listen and find that the galaxy is already singing back. Within the next 2 decades, the night sky will no longer look silent to us. Every point of light, every faint star hanging above Earth will carry a new meaning. Hidden among them, hundreds of living worlds will have been found, each one breathing its own chemistry, each one shaped by time and evolution in ways both alien and familiar. The universe, once thought to be mostly void, will reveal itself as a garden wild, ancient, and full of life. Somewhere in a quiet laboratory, the realization will dawn not as a thunderclap, but as a whisper. A scientist will sit before a glowing screen, scanning the data sent home from a distant telescope. In the patterns of light, those tiny fluctuations invisible to human eyes, they'll see the unmistakable harmony of molecules that don't belong in a lifeless sky. Methane and dimethyl sulfide, oxygen and water vapor, all locked in a delicate imbalance, that no geology could sustain. That combination of gases will tell the story clearly. Life is there, actively transforming the air of another world. The moment itself will be quiet. There will be no flash, no broadcast from the heavens, just a deep pause as humanity's oldest question receives its answer. Are we alone? The answer will be no. Not anymore. Not ever again. The discovery of life on K218b already sits at the threshold of that revelation. With a 99.7% statistical certainty, we have detected chemical patterns that fit no natural, non-biological process. The molecule dimethyl sulfide, found drifting through the hydrogen-rich atmosphere of a planet 120 light-years away, exists only where living organisms are at work. On Earth, it's made by tiny plankton and marine bacteria, the breath of our oceans turned into chemistry. On K218b, it plays the same role, whispering across the light years that biology has taken hold in alien seas. This is not a single molecule in isolation, it's part of a tapestry. Methane and hydrogen swirl in patterns that only living systems could maintain, locked in a chemical dance that defies equilibrium. If the atmosphere were dead, its chemistry would settle into balance. Instead, it pulses, restless and alive. The air of K218b is being reshaped by countless organisms, each exhaling into the planetary wind, each part of a world-spanning metabolism. Still, science demands more than wonder. The final moment of certainty will come when multiple telescopes, using different methods, see the same unmistakable signal. Independent teams will measure the same gases, rule out every alternative explanation, and find that the pattern remains. The probability of error will shrink from 99.7% to 99.99% to something beyond any reasonable doubt. When that happens, the shock will not be scientific, it will be existential. Every field of human thought will ripple. Biology will be rewritten around a new principle, that life is not a fragile accident, but a cosmic tendency. Philosophy and religion will grapple with new meanings for creation and consciousness. Technology will pivot toward communication, toward finding ways to listen, and maybe one day, to answer. Even art will change, as the idea of home expands from one blue planet to a galaxy alive with possibility. And yet, alongside the wonder will come responsibility. The realization that life thrives elsewhere will force us to ask what kind of neighbors we wish to be. If the universe is full of living worlds, then every act of exploration carries ethical weight. We'll have to learn restraint to study without harming, to explore without consuming, to share space with other forms of being that may not resemble us at all. This moment will demand maturity from our species, a humility born from the awareness that we are not the center of anything. We are one expression among many. From that day onward, humanity's story will shift. We'll no longer be a civilization that wonders about life, but one that knows. The night sky will no longer be a mystery of silence, but a map of living systems, each star a potential cradle of evolution, each planet a new experiment in the chemistry of existence. The universe will become what it truly is, not a cold expanse, but an immense ecosystem, alive with interaction and change. When future generations look back, they will mark the James Webb Space Telescope as the turning point, the moment when we crossed from isolation into community. Its discovery on K218b will be remembered the way fire or flight or the first photograph of Earth from space is remembered, as an image that reshaped how humanity sees itself. The first confirmed chemical signature of alien life, recorded in the thin light from a planet 120 light-years away, will stand as proof that the cosmos was never empty. It was waiting for us to notice. That single detection, the faintest ripple in the infrared, will mark the end of cosmic loneliness. It will be the beginning of belonging. In the hydrogen mists of that distant planet, beneath an atmosphere warmed to 120 degrees Fahrenheit, life is breathing. It may not resemble ours, no trees, no animals, no sound or movement we would recognize, but the pattern is unmistakable. It exhales, it grows, it changes the air around it. That rhythmic transformation, so subtle and yet so vast, is the pulse of a living world. And K218b is not alone. Webb's data already suggest that habitable worlds may be the norm rather than the exception. From young systems like CE Antliae, where planets are still forming from dust, to ancient red dwarfs that will burn steadily for trillions of years, the galaxy is overflowing with potential. Everywhere we look, the chemistry of life reappears. Water vapor, methane, hydrogen, carbon dioxide, all combining in endless variations. It seems that wherever nature can make life, it does. The implications reach far beyond astronomy. We are beginning to see the universe as it truly is, a network of biospheres, vast and interconnected, each shaping its environment, just as Earth's organisms have shaped ours. Oceans ripple on worlds we'll never walk upon. Atmospheres rise and fall with alien seasons. Volcanoes vent nutrients into deep seas where unseen creatures thrive. The cosmos is no longer a desert, it is alive. The technologies that open this view, Webb's mirrors, its coronagraphs, its mathematical algorithms, are only the first generation of tools. The next will go further. Within 20 years, new telescopes will scan thousands of stars, identifying hundreds of living worlds. Some will carry signatures of biochemistry stranger than anything on Earth. Life forms built on silicon or ammonia, life-breathing methane, life powered by light we cannot see. With each discovery, the boundaries of biology will expand, and our definition of alive will grow more generous. For humanity, this moment will be transformative. Every child born afterward will inherit a sky that feels different. They will grow up knowing that life exists not as a rare spark, but as a cosmic pattern. The story of the universe will no longer be the story of dust and gravity alone. It will be a story of life itself, emerging again and again wherever the conditions allow. And that realization carries something profound and humbling. Life does not seem to be the universe's exception. It is its rule. It fills the void, transforms matter, and leaves chemical fingerprints that cross the darkness to reach us. Every biosignature we detect is a message, not written in language, but in chemistry. I am here. I exist too. The James Webb Space Telescope has given us the first glimpse of this living cosmos. It has shown that we are part of a far larger narrative, one that began long before us and will continue long after. For the first time in history, we are not just looking out. We are beginning to see ourselves reflected in the patterns of other worlds. We are not alone, and we never were. The universe has been alive all along, breathing, evolving, waiting for us to listen. And now, as our instruments grow sharper and our curiosity more patient, we are finally beginning to hear it. The quiet rhythm of a living cosmos, vast beyond imagination, yet familiar in its pulse. The universe is alive, and we are part of its song.